Today, I will present my ICASSP paper, Adversarial Sample Detection for Speaker Verification by Neural Vocoders. Today's presentation is divided into 5 parts: motivation, backgrounds, proposed method, experiments, and the conclusion. Let's look at the motivation. Automatic speaker verification is one of the most important technologies for biometric identification and has been widely adopted in security-critical applications. However, speaker verification is seriously vulnerable to adversarial attacks, and effective countermeasures against them are limited. So in this work, we use neural vocoders to resynthesize audio and find that the difference between the ASV scores for the genuine and the resynthesized audio is a good indicator for discrimination between genuine and adversarial samples. Let's get into the background. Let's see the ASV workflow. Given a testing utterance XT, the ASV will compare it with the enroll utterance XE by feature extraction and the similarity comparison to decide whether accept or reject the testing utterance. A well-trained ASV model can do the speaker verification very well. However, some in the wild attackers will try to do an adversarial attack to deceive the ASV. Let's see the attack procedure. For simplicity, I do not show the enroll utterance here and only show the testing utterance here. Here, X is the testing utterance, and we take the non-target trail for example. In the non-target trail, given X, the ASV should reject it. However, attackers can do adversarial attack by crafting very small adversarial noise delta, adding such noise to clean sample X to generate adversarial sample X delta, and then fooling the ASV to falsely accept it. But still, X delta, the adversarial audio, is very similar to X, the original audio from humans' ears. So far, the attackers can fool ASV models, which is very dangerous. And in this paper, we propose to detect the ASV models by neural vocoders. In section 3, I will show the proposed method. This is the proposed detection framework based on neural vocoders. We will not show the enroll utterance and only show the testing utterance here. The testing utterance is X. Given the input utterance X, be it genuine or adversarial sample, there are 2 paths. In the upper path, the ASV will output the score S, and in the lower path, the ASV will the X will pass through the feature extractor and the vocoder to get the resynthesized audio X delta, and X delta is fed into the ASV to get another score as prompt. Finally, we get the absolute value of X as prompt minus S. If you know X is a genuine sample, the vocoder will do nearly lossless reconstruction. Loss X is very similar to S prompt, and we will show the phenomenon in the experiments. But for the adversarial sample, the vocoder will try to purify the adversarial sample. Thus, S prompt is far away from S, resulting in larger absolute value of S prompt minus S. We use the absolute value to distinguish whether a sample is genuine or adversarial. Let's see how to how to use the framework to detect the adversarial samples. We want to find a threshold tau for detection. If S prime minus S is larger than tau, the input X will be classified as adversarial samples. Let's see how to find tau. We have the clean sample set T genuine. We have the clean samples X genuine 1, X genuine 2, and X genuine I. We want to calculate all the absolute value of S minus S prime for genuine samples. Here we denote this number as D. Then we get the D for each genuine sample. Then given a false positive rate for genuine samples, be it 1% or 5%, we can get a threshold tau as this equation. And then we get the threshold tau for detection use. And during inference, when given an input X, we can get the absolute value of S prime minus S, and we compare it with tau. If it is larger than tau, we will classify it as genuine and filter it out. Here is the rationales of the proposed method. As the vocoder is data-driven and trained with genuine data during training, it models the distribution of genuine data, resulting in less distortion when regenerating genuine samples. And during inference, the vocoder's preprocessing will not influence the ASV scores of genuine samples too much. When the inputs are adversarial samples, the vocoder will try to pull it back to the manifold of their genuine counterparts, resulting in purifying the adversarial noise. This figure reveals the rationales. Here, x-axis is the absolute value of S prime minus S, y-axis is the amount of samples. We have 4 curves, 2 for neural vocoders and 2 for Griffin limb. Let's take the dashed line for example. The green dashed line denotes the genuine sample, and the red dashed line denotes the adversarial samples. We have the following observations. The score difference for genuine samples is near 0, while the score difference for adversarial samples is much larger, and we can simply set a threshold here to distinguish them. And we can get the same phenomenon for the Griffin limb. Let's get into the experiments. For the setup, we use ResNet as our speaker model, and it is trained by Vocoders 2 dataset. And the Vocoders 1.0 dataset is adopted as the evaluation set. We use the basic iterative method to generate adversarial samples. And we use a traditional vocoder, the Griffin limb, and a neural vocoder parallel wavegain for detection. This table shows the equal error rates for ASV equipped with different vocoders. None means only using ASV model. Vocoder Griffin limb linear, Griffin limb male means the ASV systems equipped with parallel wavegain, Griffin limb linear, and Griffin limb male. This row shows the attack budget. The higher the value is, the more powerful the attack is. And here, 0 means no attack. We have the following observations. When testing on genuine samples, the equal error rate is 2.88%. When using generated speech as input, the equal error rate slightly increased. Well, introducing the adversarial attacks, the equal error rate increased from 2.88% to over 70%, which shows the effectiveness of the attack method. And the vocoder has slightly purification performance. However, the resynthesis process will not affect the genuine equal error rate too much. This table shows the detection with different methods under different false positive rates. We have four false positive rates here, and we have 4 detection methods here, and we have the following observations. We found that using vocoder performs the best among all methods, and also in most of the cases, more than 90% of the adversarial samples could be detected. And for Griffin-Lin-based methods, we found that they might be good approaches for detection with a large positive rate. However, in stricter cases, the detection rates decrease drastically. Let's see the conclusion. In this paper, we adopt a neural vocoder to detect adversarial samples for ASV. The proposed method achieves effective detection performance. And for the future work, we will evaluate the detection performance when the detection method is known to the attackers. That's all I have. Thanks.